The world's very first failed attempt at nuclear fusion might have just had an overhaul over a century later. A revival that could beat all other fusion technologies to the grid with the most compact reactor in the world without the billion-dollar price tag. Without using magnets, no need for superconductivity, no heating, no crazy lasers. Just a good old zap of electricity. Did we just figure out how to control Zeus's lightning in a reactor core on a shoestring budget? Let's figure this out together. I'm Ricky, and this is 2-Bit Da Vinci. This video is brought to you by Jackery. Right now, a company called Zap Energy is operating a machine that defies the conventional wisdom of nuclear physics. While the rest of the world is building fusion reactors the size of stadiums like the massive $22 billion ITER project in France, Zap Energy is building one you could fit in your garage. They're using a technology called the Z-pinch. It's a method of nuclear fusion that compresses hot plasma using a self-generated magnetic force. This technique lets you strip away all the complexity. You get rid of the superconducting coils that need to be cooled to near absolute zero. You get rid of the natural beam injectors that TAE uses for its field reverse configuration machine. They rely on a simple, brutal pulse of electricity. They run a current 10 times stronger than a bolt of lightning through a column of hydrogen gas. This current generates a magnetic field that crushes the gas into a tiny, super hot filament where fusion happens. But here's the catch, and it's a big one. According to physics history, this machine shouldn't work. For 70 years, scientists have known that trying to squeeze plasma like this is trying to compress water with your hands. The plasma should tear itself apart in millionths of a second. And for decades, that's exactly what it did. But Zap Energy's found a way to control it. The solution is called shear flow stabilization, and it's the single reason we are talking about this company today. Zap's founders spent 20 years at the University of Washington perfecting this. The idea is to stop treating the plasma as one solid block. Instead, they manipulate the flow so that the plasma moves in layers, kind of like a highway. Imagine being in the center lane of a freeway at 50 miles an hour. The lane to your left is moving at 80 miles an hour, and the lane to your right is moving at 100 miles an hour. Can you change lanes? No. The difference is speed. The shear locks you in place. You're effectively trapped in that center lane. Zap applies this logic to the plasma. They create a flow profile where the outer layer of the plasma are moving faster than the inner layers. When the central plasma tries to bulge or kink, which is a specific instability that killed the Z-pinch in the 1950s, the fast-moving outer layer shears it back into alignment. This smooths out the instability purely through fluid dynamics, no external magnets required. This allows them to keep the plasma stable thousands of times longer than previous attempts, long enough to fuse. By solving the physics with software and fluid dynamics rather than brute force hardware, they unlocked a massive advantage: speed. Because their reactor doesn't need those massive superconducting magnets or building-sized lasers, they can design, build, and commission a new machine in just 1 year. And they can do it for a cost of just $1 million per prototype. This allows them to iterate faster than anyone else in the industry. While other projects take decades to build a single test reactor, Zap is churning out prototypes. They have already managed to generate thermonuclear fusion in Deuterium-Tritium fuel, a world first for this technology, and they are incredibly close to reaching net energy gain. Before we crack open the reactor to see the genius inside, we need to understand why this approach is so promising compared to everything else. In fusion engineering, we live and die by the triple product. It's a simple equation: density times temperature times time. To get fusion reactions that produce energy, you need to get the product of these three numbers high enough. Every fusion approach compromises one of these variables. One is magnetic confinement, tokamaks. These machines, like ITER, are like slow cookers. They reach moderate temperatures for a very long time, seconds or minutes, but the plasma density is very low. 2, there's inertial confinement, using lasers. These machines, like the NIF, are like explosions. They reach incredibly high densities and temperatures, but for a tiny fraction of a second. Zap Energy's Z-pinch sits in the Goldilocks zone. They reach moderate temperatures and densities for moderate amounts of time. And the data shows that they are remarkably close to the finish line. This is truly a golden age of sustainable tech. And when it comes to tech that you can actually buy today, our sponsor Jackery has you covered. These are my 3 favorite things that I saw at the Jackery booth at CES. First, the new Jackery Solar Gazebo. This beautiful and metal gazebo houses 2,000 watts of solar panels on the roof with built-in lights, fans, louvered shutters, and retractable shades. Enjoy the outdoors in style. I love the look, and having gotten a quote recently for a backyard patio, I really think this is a great value. Combine this with the Jackery Explorer 5000, and you have outdoor power without trenching or expensive electrician visits. Second, and probably my favorite, is the Jackery Solar Mars bot that autonomously follows users, avoids shade, and tilts to track the sun all day long for maximum production up to 600 watts of power. Whether it's camping trips or festivals or even emergency response, this awesome bit of tech provides power wherever you need it. Finally, the Explorer 1500 Ultra, a true workhorse in portable power. Rugged, portable, and all-weather, you can take this thing anywhere. It's IP65 rated, dustproof, and waterproof, and Jackery always makes some of the lightest and smallest batteries in each category. Now, this is my go-to battery for things like powering my Starlink or my computers, lights, and camera gear, e-bikes, and all that sort of stuff on travel. They have a ton of new amazing releases. Learn more about Jackery's awesome new lineup using our links in the description for the best prices today. Huge thanks to Jackery and you. Now back to the show. Their current machine, Fuse 3, is operating at 500,000 amps of current. At this level, they are already fusing atoms, but the magic number is 650,000 amps. At that specific current, their models predict they will reach Q equals 1, or scientific breakeven. That is the holy grail where the energy coming out of the fusion reaction equals the energy put into the plasma. They're just a 30% power boost away from a milestone that eluded scientists for decades. And unlike the National Ignition Facility, which claimed net energy but ignored the massive inefficiency of their lasers, ZAP's efficiency calculations are direct: electricity in versus electricity out. If they push that current to roughly 2 million amps, their model predicts a Q of around 30. That means for every 1 unit of energy they put in, they get 30 units back out. And that would be a commercial power plant. So how do they do it? How do they control a miniature lightning bolt without it blowing apart? Let's put on our lab coats for a minute and break down the physics, because this is where the engineering insight really shines. The reactor itself is a vertical column about 3 meters tall. It looks a bit like a vortex cannon. You inject the fuel mixture, deuterium and tritium gas, at the top. Then you hit it with a massive pulse of electricity. This effectively turns the gas into a plasma and accelerates it down the column. The central rod in the machine ends in a nose cone, so the plasma shoots out the end into the empty part of the vacuum chamber, forming a long, thin column. This is where the Z-pinch happens. It unfolds in a specific sequence of phases. Phase 1, an electric field is applied along the gas column. Phase 2, this causes electrons and positive ions to flow in opposite directions. Phase 3, this flow of current generates concentric circular magnetic lines that wrap around the plasma column. Phase 4, these magnetic field lines interact with the moving charged particles. This creates a Lorentz force. Using the right-hand rule, we can see that this force points directly inward toward the center of the cylinder. Phase 5, every particle in that column feels a crushing force from all sides. Phase 6, the plasma collapses. This magnetic vice grip compresses the plasma into a filament that is only 1 to 3 millimeters thick. It is hot, it is dense, and this is where the fusion happens. But as I mentioned earlier, this is where physics usually fights back. In a normal Z-pinch, that tiny filament creates sausage and kink instabilities. It tries to bulge out or twist. This is where Zap Energy's secret sauce comes in: shear flow stabilization. But the engineering genius doesn't stop at the plasma. It extends to the reactor wall. If you are generating a mini sun inside a metal can, how do you stop the walls from melting? And how do you harvest that energy? Zap uses a liquid metal wall. The reactor chamber is lined with a flowing river of molten lead and lithium. This is the brilliant engineer's choice for 4 distinct reasons. 1, it's the electrode. The liquid metal acts as the outer electrode to complete the electrical circuit. 2, it's the shield. It absorbs high-energy neutrons and radiation so they don't leak out and irradiate the facility. 3, it's the coolant. It acts like a heat sink. It carries the intense heat away from the core to a heat exchanger, where it can generate steam and electricity. 4, it's the fuel factory. This is the coolest part. Deuterium is abundant in the ocean, but tritium is radioactive and scarce. When the fusion neutrons hit the lithium in the liquid wall, the interaction breeds tritium. Zap can extract that tritium and pump it right back into the machine as fuel. And because it's liquid, it's self-healing. A solid wall would get brittle and crack under neutron bombardment, but the liquid simply flows. They even optimize the chemistry. By using a eutectic mix, roughly 16 lithium atoms for every lead atom, they lower the melting point of the lead from 327.5 degrees Celsius down to 235 degrees. This means they waste less energy just keeping the metal molten. To really appreciate how revolutionary this is, we have to look back at why this revival is so historic. The Z-pinch isn't new, it's actually ancient. The phenomenon was first observed way back in 1905, when a lightning bolt struck a hollow lightning rod in Australia and crushed it flat. In the 1950s, the Z-pinch was actually the very first approach scientists tried to control fusion. It was Project Sherwood's preferred model. It was the original dream, simple, compact fusion. But that kinking issue was just catastrophic. The plasma would pull off and die in nanoseconds. After 7 years of failure, the scientific community gave up. They pivoted to using massive external magnets to force the plasma to behave. Thus, the tokamak was born. Costs skyrocketed, and the Z-pinch was forgotten. ZAP isn't inventing new physics. They are fixing the oldest one. They're redeeming a 70-year-old failure with modern fluid dynamics. Now, I'm an engineer, not a hype man, and we have to look at the numbers and the hurdles and be real about this. Tokamaks like ITER have budgets that have ballooned to over $22 billion. The National Ignition Facility is roughly around $3.5 billion. And ZAP Energy? Well, they raised about $327 million in total. So how's it so cheap? It's the magnets. In a tokamak, the magnets alone cost around $400 million. ZAP's magnets are the plasma itself. This means their capital cost for a power plant would be 2 orders of magnitude lower than a tokamak for the same output. We're talking about a reactor core that costs just a few $1,000,000. A typical 1 gigawatt nuclear fission core costs over $1 billion. ZAP could slash the capital cost by over 90%. But what's the catch, right? What's stopping them from doing it right now? The barrier isn't the reactor core anymore. It's the switching. To make this a viable power plant, you can't just fire it once. They need to fire it repetitively. To match a small nuclear power plant, they need to fire roughly 10 times every second at 10 hertz. This means switching 650,000 plus amps on and off 10 times a second, continuously for years. The power electronics required to handle that kind of load without melting are incredibly complex. Currently, the fuse machine operates at a relatively mild 10 to 20 kilovolts. To get the currents that they need, they'd have to ramp it up to around 30 kilovolts. These high voltages put a massive strain on the switching devices. However, compared to the challenges facing other fusion companies like TAE, which needs to increase neutral beam power by several orders of magnitude, ZAP's hurdle is just a 50% increase in voltage. It's an engineering challenge, not a physics miracle. And they're already working on it. ZAP isn't just running science experiments, they are building a product. They're currently constructing Project Century. This is the world's first 100 kilowatt scale repetitive Z-pinch device. It's a fully integrated system designed to test the durability of the liquid walls, the electrode, and the switches. They've already proven they can fire the power driver once every 10 seconds for 3 hours straight without a single fault. That is reliability data that most fusion startups can only dream of. If they succeed, we are looking at a future where fusion energy isn't generated in massive centralized plants that take a decade to build. We're looking at modular factory-built reactors that can be deployed anywhere. It's a vision of a democratized power grid powered by the most energy-dense fuel in the universe. And ZAP Energy is betting that the solution to our energy future isn't bigger, it's smarter. But what do you think? I know we've made videos about fusion for years, but this does feel different, and it does feel like the rate of progress and development is happening faster. But what do you think? Are we at the doorstep of a revolution in fusion, or is it just another cool science experiment that is 20 years away like everything else? Sound off in the comments below. And if you thought this was cool, we have some other really awesome videos that we think you're going to like. If you're new to the channel, please consider subscribing and join us, join our Discord, and join us for all the future stuff that we got planned. It's going to be an amazing year here in 2026. Thank you so much for watching, and we'll catch you next week.